All right, so differential calculus. All right, so maths methods, as I've said, covers the initial part of this in detail, and three things that come out of methods that we will be using is some rules that we will use. So these rules, the first one is called the product rule, and you get the product rule, you use that when you have two functions multiplied. Alright, and the product rule says this, so the derivative with respect to x of u times v, so u and v are our two functions that we're multiplying together, and the rule that's used, the pattern, is that it's function u times the derivative of function v plus function v times the derivative of function u. Okay, and so in methods you'll go through in a bit in detail how we get that, how that works. Then the next rule that we use is called the quotient rule, and we use that when we have two functions divided. And so if I have the derivative of u over v, the rule ends up being like this. Function v times the derivative of u minus function u times the derivative of v all over function v squared. Alright, and again in methods we'll go into detail in methods where that comes from, how we get that. Now these are on the formula sheet at the end of the year. You don't need to remember them, just how to use them. Alright, got that, have we? Rub off. Alright, the third rule that we're going to use is called the chain rule. And the chain rule, we use that when we have one function inside another. So like fog and golf. So if we have dy dx, so this one is dy du u times du dx. You might be thinking, where's the function inside the other? Well, u would be a function, and that's inside that makes up the y.
What?
Hmm?
Is that?
So u is a function,
Yeah.
and that's stuck inside something else to make up the y. So, like for example, u might be x squared, and we might have y equals sine of x squared. All right, so you've got a function, x squared, inside another function, sine. And so we use the chain rule when we have that kind of thing. Any questions? No? All right, so we need to use these things. All right, today what I am going to, we're going to look at is, first up, the derivative of tan. So in methods we'll do the derivatives of sine and cos. But not tan. So if we're using the tan kx is equal to sine kx over cos kx, and then the quotient rule, what we get, so I'm not going to go through all the working out for that, but U and V, use that rule, collect like terms, cancel what you can, etc. What you're going to get in the end is that the derivative of tan kx is equal to k times x squared kx. All right, so the pattern with tan kx is that. Now that's, again, that's on your formula sheet. All right, so there's a few things on the formula sheet. The normal polynomial, exponential, log, sine, cos, tan. They're all on the formula sheet. All right, so what we're going to do is use that pattern, that relationship. All right, you could also use the from first principles and get that, but that's very messy and takes quite a long time. All right, so the first example then. We're going to differentiate y equals tan of 6x. If we follow that pattern, dy dx would be, all right, pattern says that your constant comes out the front, 6 times with 6 lots of what? 6 lots of x squared 6x. Okay, so now let's start to use some of these rules. some. All right, if you're not sure about anything, make sure you stop me. Because I have this background is not quite what we might like.
So that's the answer.
So that's the answer. Yeah. All right, so, if we use the chain rule or first principles or whatever, be a lot of working out, take a long time. But yeah, in the end we see that there's a pattern, so we're going to use the patterns. So the pattern for differentiating tan is this constant comes out, and then we've got sec squared, what's in that bracket. All right, so that's when what's in the bracket is simple, but if what's in the bracket is not simple, then we need to use some other techniques. So let's have a look at a couple. Oops. So differentiate. All right, so if I have something like so in this example, A first of all. So in this example, we've got something that's more complicated inside. This tan here is just straight 6x. Now we've got something more complicated. So now we need to think about it and say, okay, well, looks like we've got a function, 5x squared plus 3, inside this tan. So because we've got 5x squared plus 3 is inside tan, what that means is that we use the chain rule. Alright, the chain rule is dy dx is dy du times du dx. And then we've just got to decide what it is we're going to make our u, and it's always the thing that's inside. So whatever's inside this bracket here is the u. So we're going to say, okay, so let's let u equal 5x squared plus 3. And as you can see over here, we need a du dx. Who can remember when we differentiate a polynomial, what happens? Yep, so our power comes and times us by what's there, so 2 5s are 10, and it reduces by 1, and a normal number plus 0, and normally we wouldn't write plus 0. So if we're replacing, writing y there is equal to tan u, if we differentiate with respect to u, then what we've just done says the constant. No, there is no constant here, it's 1, isn't it? So it's 1 out the front, sec squared of u. Alright, now we put those things together, so dy dx. So it's dy du times du dx. So dy du is sec squared u, and du dx is 10x. Now, last thing I need to do is substitute that. Question?
No. All good.
Alright, so now because I'll let u equal 5x squared plus 3, final answer I need to have it in terms of x. So that's what we started with, so it's x squared, 5x squared plus 3 times 10x, and probably we'll see the 10x at the front. And so that would be how you probably see the answer. Alright, so we've got a function inside another one. We use the chain rule. All right. I'll rub that off. B. 6 squared. Now, when we are looking at excuse me, when you look at your list of standard derivatives, sec squared's not one that's on it. So we need to do something else. So we've got y equals sec squared of 3x. So we need to do something else with that. So Pythagorean identity. What is the Pythagorean identity? Sine squared plus cos squared equals 1.
Yeah.
Yes? Now if I take that Pythagorean identity and I divide by cos squared, I end up with tan squared plus 1 equals 1 on cos squared, and 1 on cos squared is sec squared. So this here I'm going to rewrite using this from the Pythagorean identity. There's also another version of it, but it's the one we're using. If you divide by sine squared, you get another variation. But because we've got sec squared here, sec squared is 1 on cos squared, so I've divided by cos squared. Alright, so rewrite that then. So instead of sec squared, we're going to have tan squared plus 1. So it's tan squared of 3x plus 1. And now I've got a bunch of stuff going on here. All right, any ideas?
Have you got, would you use the chain rule?
You do use the chain rule, yep. You do use the chain rule, but what are we going to make u?
3x.
Yeah, this one's a tricky one, because we're not going to make u 3x. So what does tan squared 3x, what does it actually mean? What it actually means actually means is the tan of 3x and square it. Alright, so that's the way we write that. So, when you think about tan squared of 3x as being this, which one's on the inside? Which one's on the inside? Tan 3x is on the inside, yes? So this is the one on the inside. Do we know how to differentiate tan 3x?
Yeah.
Tan kx, yes, we do.
Yeah.
Alright, so again, it's only when, if it's just x there, we can differentiate that. It's only when it becomes x squared or something more complicated. Alright, so yeah, as I said, this one's a tricky one and people do get tripped up by it. So what we're going to do is we're going to let u equal tan 3x. And so du dx is 3 sec squared 3x. Then, if we're letting u equal tan 3x, then what means that y will become u squared plus 1. Would that be correct? And when we differentiate that with respect to u, I believe. Then put all of that together, so dy dx. We just multiply these two things. So 3 sec squared 3x times 2u. Now instead of u, I'm going to replace the u with the tan 3x. We're all good with that? So we've got 6 sec squared 3x tan 3x. Right. Anything you want me to clarify there in that one?
Would you get rid of the sec squared or just leave
Might
it?
as well just leave it. Because what would you do? 1 on cos squared.
We could do tan squared.
I mean,
Oh, that wouldn't change.
I mean, you could, there's a whole bunch of stuff, you know. It could be 6 times 1 on cos squared, and then you got sine on cos, so you could have 6 sine on cos cubed, but you know. So you could fiddle around with that, but I don't think anything that you're going to fiddle around with it to get is necessarily going to be any better. All right. All right, another pattern that we're going to do in methods in more detail is, as I mentioned, exponential before, so here's an exponential question. All right, so we're going to differentiate an exponential. Now, pattern for an exponential is that ke to the kx. So from that, if we were to differentiate, say e to the x, it's simply e to the x. All right, so that's a pattern again. That pattern's on the formula sheet that you get. But this time we've got this little extra added thing in here, and it's not just x, it's x squared. So we've got x squared, which is a function, and then we're doing something to that. We're doing e to it. So whenever we've got, again, a function inside another function, right, so we're doing e to the power of to the x squared, so we do the x squared first, then we e it, e to the power of it. So u is going to be x squared, yep. And so du dx will be 2x. And so then we've got to differentiate with respect to u, e to the u, which is e to the u. Yes? So d dx of e to the x squared then is multiplying these two things together. So it's 2x times e to the u, put the x squared back.
And why isn't it? I don't know why that makes sense. Don't worry. Sorry.
What I'm from
I
the other
thought
way
why
around.
wasn't it UE, but U's not KU there.
Yeah, 'cause you can think about what, if you've got a number for x, say 5, what do you do with the 5? You square it first,
Yeah.
and then you do e to the 25. So the thing you've done first is your u. Yeah? Like when I had the tan of all of that 5x squared plus 2, what do? You take your x, you square it times 5 plus 2, you do that first,
Yeah.
then you tan it. So the thing you did first is your u.
Okay.
Yeah? Is that
Yeah,
a
yeah.
better way of thinking about it?
Yeah, no, I was wondering, I thought U was K. The was a K value instead of X.
Oh yeah, use this.
Yeah. Yeah.
So that's why I put that back there.
Yeah.
All right, so that's that one. All right, one more example. And that is the derivative of log. Again, we'll do this in methods. Can I rub all that off? I said no quick enough. So the pattern that involved for the derivative of log log to the base e of the magnitude of x. Because you can't take the log of negative numbers, it doesn't exist. And that relates to log graph. So we look at often the magnitude, just the size of the x. So if, now here's a different way of writing it. So I used y and x before, and so I did y to x. But if I use function notation, fx, then if fx equals log to the base e of the magnitude of x, then the derivative, and we do that as f dashed x. So the dash there, f dashed x means, so all of this here means the derivative. All right, that's just your function notation, right? The other one's called Leibniz notation, but this is function notation, and this little dash here, it's a dash, not a 1, it's a dash, indicates that. And so the derivative of log is 1 on x. And so, again, that pattern is on your formula sheet, and then we need to use it. So let's have a look at an example.
So is this the chain?
We'll use the chain rule, yep, because what are we doing? We take our x, we find the sec of it, then after that we take the log. So chain rule, because the sec is inside the log. It's not log of something times sec x, it's the log of sec x. So chain rule again. And so, yeah, the bit that's on the inside is our u. And y would be log to the base e, the magnitude of u. All right, I'll do the easy one first, that's this one. So if I differentiate y with respect to u, simply just 1 on u. Oops. Which is 1 on sec. And 1 on sec is going to become, it is going to become cos. Because we've got 1 on sec, and sec, of course, is 1 on cos. And when we are dividing, we flip and multiply, so that one just simply becomes cos. All right, so that was reasonably straightforward. This next one, because there's no pattern on our sheet that tells us about sec, we need to rewrite that. So we need to say that it's 1 on cos x. Now, we've got the cos at the bottom. So if the cos is at the bottom, we need to use the quotient rule. Because it's 1 divided by cos x. So we need to use the quotient rule here. All right, we've got to assign a u and a v.
Now, can you explain why we need quotient rule, sorry?
Because, well, here when we've got this, we've got 1 divided by cos x.
Yeah. Oh, so it's, again.
So because we're dividing by a function,
Yeah.
that's where the quotient rule comes in when we're dividing. All right, so what's what? So whatever's on the top is our u, whatever's on the bottom is our v. All right, so let me use some other letters. Can I change and use some other letters? Because I don't want to confuse this u and this u. So what are we going to use as that u there? Instead of that u, we're going to use a w. All right. Great idea. All right, so quotient rule says, back to it. And then we'll rewrite it. Quotient rule says u over v says v times the derivative of u minus u times the derivative v over v squared. And so what we're doing is instead of using u, we're using a w. So that's a w there, that's a w, and that's a w. We're all good with that? So we don't lose ourselves. All right, so w is equal to 1. What's the derivative? When we differentiate 1, we get what do we get?
0.
0, yes. All right, v is cos x, and when we differentiate that, if you look up your patterns on you get negative sin x. You look that up on your formula sheet. All right, now we've got to put it in there. So the derivative, this one here, derivative of that one, so the derivative of this here. All right, v times the derivative of w, so v is cos x times 0 minus w, which is 1, times the derivative of this, all over v squared, and v is cos, so it's cos squared x. Which becomes all right, cos x times 0 is 0. Negative 1 times negative sine is sine. All right. So that's du dx. So got to think about what we were after at the start. We're after the derivative of this thing. Yes.
Was it supposed to be dw or du?
Du, so it's a
Oh, okay.
differentiating that.
Yeah, thanks.
So, yeah. All right. So dy dx is dy du times du dx. And dy du is cos x, and du dx is sin x over cos squared. And what happens here? Anything exciting here? Got some cancelling? This cos x with one of those. And so we have 10. All right, so a lot of fiddling around to get our answer. Question?
made this up?
Hey? Who made it up? Oh, it's exciting, isn't it? Isn't that great?
There's so much work in
So we're in that. That's a fairly involved process. So if I've lost you somewhere.
Does it get harder than this?
Oh. On exam 2, there's probably some more complicated functions that you would do, but you'd use your calculator to do them. So, that took us a fair bit of time. So, it's not likely that they're going to ask you in exam 1, because remember, exam 1's only an hour.
How long is it going to
2 hours. So something like that takes a fair bit of time.
Yeah.
So you would hope that exam 1 is going to be something that's a little bit more straightforward than this one. All right. That's it then.